Hello viewers, welcome to this new video on strength-stiffness dependency. The strength is imparted in the structure so that it can resist the external actions, and stiffness is imparted so that it can resist the deflections or displacement. Now, are they related to each other? Let us explore this in this video. So let us go back to the definition of stiffness. Stiffness of a system is the force required to produce unit displacement in the system. So if this is the definition, then we can write certainly stiffness by denoting it by K equal to F divided by delta. So we have taken a force deformation diagram or force displacement diagram response for a particular structure or a structural element. Let us consider any point here on the force deformation diagram. This point B is considered. So at this point B there will be corresponding force here. Let this be force be small f, and corresponding to this point B the displacement is small delta. So definition hold good, so we can write K equal to the small f by small delta, so which is nothing but OA divided by OC. That is what is written here. But because it is a parallelogram here, so OA will be equal to CB, so we can write here CB or BC divided by OC. But if you consider the triangle OBC and you take the ratio of BC divided by OC, then it is nothing but the tangent of the angle. So we can write again K equal to tan theta. So it indicates the stiffness of a system is equal to the slope, tangent of the slope of the force deformation diagram. So that is what we have written here. So when you design something, you design a structure or a structure element, actually internally you are doing three entities. So these entities are, one is the strength. Strength is the resistance against external actions. And also you design for stiffness. Stiffness is the resistance against displacement or deflection. Unless an adequate stiffness is there, your structure will deflect so much that it will not be useful for the purpose you have designed it for. And you also design for ductility so that your system is undergoing large deformation without failure. So let us understand what are the implications within this. So strength is a function of the sizes, the width of the section, the depth of the section. Then it is the material characteristics, the yield strength Fy, and or if it is concrete then FCK, and if it is concrete then percentage steel. Then shape, whether it is rectangular or other sections, I sections, it will depend on that. And detailing. Now how detailing will be affecting the strength. Suppose you put a small amount of steel at a large effective depth, you get a moment of resistance. Again, if you take small effective depth and large amount of steel, you may get the same amount of moment of resistance. So detailing or the position of the steel is also affecting the strength of the section. Stiffness is a function of the sizes, the breadth, the depth, and it is also affected by the modulus of elasticity and the shape, whether rectangular section, I section, etc. Ductility is actually not affected by all this generally, but it depends on the detailing and disposition, both in concrete structures and steel structures. In steel structure, you have to keep attention to the joints specifically for ductile system. And in RC structures, the country codes are there which will be giving you the detailing requirements so that the system is ductile. Though a little effect will be there of the depth of the section, we will see later on that depth will be affecting the ductility also. So strength is imparted through design. The design we learn in our RC design or steel design. So through the design process, strength will be imparted so that it can resist the external actions. Stiffness will be imparted through mechanics and design, that is how much modulus elasticity I to be provided so that the system undergoing deflection is within the limit provided by the code. And detailing cannot be designed, or you cannot go through mathematics for imparting ductility, so it is imparted through only detailing. Now let us again revisit the strength. For say concrete section, the strength can be given by m equal to q bd square, the moment of resistance formula. Within q you have the effect of Fy and Fck for a concrete section, and you have the effect of the breadth and depth here, effective depth. Similarly, moment of resistance can be given in terms of steel. In that case, moment of resistance is given by the second formula, where the area of steel is coming into picture, Fy is coming into picture, and the distances, the lever arm and the neutral axis depth. For a steel section, moment of resistance is given by permissible bending stress into modulus section Z equal to I by Y. So these are the strength formulae practically. Now stiffness we have studied in previous video. Axial stiffness is given by AE by L. Rotational stiffness is given by 4EI by L. Stiffness against deflection of one end of a beam is given by 6EI by delta square, 6EI by L square. And stiffness of column against lateral sway is given by 12EI divided by L cube. So if you compare these two, in strength Fy is in bold, Fck is in bold, area of steel is in bold, and the dimensions in bold, as we have discussed in the previous slide. In stiffness, Fy does not come into picture, Fck does not come into picture. Of course, breadth and depth are coming through the this moment of inertia I. And new term, the modulus of elasticity is coming into picture, and the system length, the length of the beam, length of column, etc. also coming into picture in the stiffness. So question is whether they are related or not, whether stiffness and strength will be related. In the stiffness, Fy is missing, Fck is missing, Ast is missing, and new thing you are getting is the length of the members. So whether they are related to each other or not, whether one is affecting the other, that is our question. For that purpose, we seek the help of moment curvature diagram. Moment curvature diagram is the representation of moment versus curvature of a beam section. So one beam section arbitrarily we have taken, and the vertical axis is the moment axis and the horizontal axis is the curvature axis. So it is in the beginning straight line, linear, then after yielding it will become non-linear, and this is the moment curvature diagram. So when the yielding starts, we may say this is the yield point, and corresponding moment in the moment axis is the yield moment My, and corresponding curvature in the curvature axis is yield curvature phi y. But in some cases you may not see any visible yield point in the force deformation moment curvature diagram. In that case, you have to proceed in a slightly roundabout way. A little nonlinearity is seen here, that's why it is called initial yield point. So what you do to get the actual yield of the system, which is a consensus amongst the engineers how to calculate the yield. So you draw a line OA tangential to the original line, original moment curvature line, and draw another line AB horizontal in such a way that the area above this line and area below the line are equal. These two areas are equal. This is coming from the energy principle, that energy you are excluding and you are taking are same, so that it is not violating the mechanics. So where the two lines OA and AB intersect is the point A here, which is your yield point. So this is the consensus among the researchers and the engineers, so that the yield point is found out like this. Then correspondingly you have the yield moment my, and on the curvature axis you have the yield curvature phi y. Now let us consider a section having certain width b and some depth here, and we consider some percentage steel. For the sake of convenience, let us keep the compression steel same and this tension steel percentage PT we shall be gradually increasing. So in the beginning I have taken 0.5% steel in the section. So moment curvature diagram I shall draw for this beam section, and it will be, when you have bilinearized it or idealized it, it is having a straight line rising, then it is flat line, and this is the yield point. So corresponding to this tension steel percentage 0.5%, let the yield moment be my1. Now what you do, I increase the steel in this section at the bottom, that is PT I increase, and here you are getting the yield moment, and we have drawn a line here. So in the next section we have kept the size same, only we have increased the tension steel here to percentage 0.75%. And again we shall draw the moment curvature diagram for this section, and you get this line. Now the yield moment is my2, and it is higher than the my1 because we have taken more steel. So strength is increased, so that's why strength is reflected in the yield moment, my2 is higher. But the yield curvature has not changed, it is remaining the same point. We take another case with percentage steel 1% and section size same, and get the moment curvature diagram. This is like this. The yield moment is now my3, which is higher than my2, but the yield curvature remains at the same point. I take another section with higher steel, say tensile steel percentage 1.5%, and draw the moment curvature diagram. I get another diagram which is having higher location, so my4 is still higher than my3, but the yield curvature remains same. So this is a phenomenon obtained from reality, that for the given section, if you have not changed the sectional size, then the yield curvature does not change. But if you go on increasing the steel amount or increasing the strength of the section, then the yield moment is gradually increasing, and side by side the slope of the lines are changing. We have seen in the previous slide that the slope of the line indicates the stiffness. So we have this conclusion is for the same section, increase of steel increases yield moment, but yield curvature remains same. This is what we have found here. Now let us see why it is remaining same. The reason is, in the literature you will get relationship between the phi y yield curvature and the size of the section D. So if D is kept constant, and the steel variety is kept same, then the yield strain of the steel will remain same. Yield strain is equal to Fy by Es. So this will remain constant, and if you do not change the sectional depth, then D remains constant and yield curvature remains constant. So whether you increase the amount of steel gradually, this formula is not going to affect it, and yield curvature, that is why it does not change for a given section with the increase of strength. So this we want to verify further and understand what is going on inside. The previous diagram we have drawn here in a different scale. So I have this blue curve for the percentage steel 0.5%. My section is this, which is not changing. The percentage steel is changing. I have not shown here because it will be changing gradually. Then when the percentage steel is higher, your curve is raised to this level, yellow curve. Percentage steel 1%, it is raised to this red line, red curve. And for 1.5% steel, the green curve is drawn. These are moment curvature diagram lines. As we observed earlier, the yield curvature does not change, so phi y line is constant here. Now, the angle subtended by these initial state lines with the horizontal, if you take tangent of that angle, it gives the stiffness corresponding to this force deformation diagram or moment curvature diagram. So, for the first line, you have this tangent of this angle will give you the stiffness K1. For the second line, for steel percentage 0.75%, you get the tangent of this line say equal to K2, and similarly for third one K3 and fourth one K4. Since the angles are changing and increasing, the tangent of that angle is also increasing, so K1, K2, K3 are gradually increasing in magnitude. So that is what we can write. And similarly, as we have seen, the corresponding yield curvatures MY1, MY2, MY3, MY4, where MY4 is highest. So we can write this MY4 is greater than MY3, greater than MY2, greater than MY1. And from this tangent of the angles, K4 is greater than K3, greater than K2, greater than K1. So what does it indicate? Indicates that as you increase the strength of the section without changing size, as you increase the strength by increasing the percentage steel, the stiffness also goes on increasing. Okay, so this is what we are getting from the reality, from the moment curvature diagram, actual behavior. Now let us see what the code is assuming regarding this. The code assumes that your section having some stiffness which is given by B and D, that is, if it is a rectangular section, I equal to BD cube by 12, and is guided by only these sizes B and D. Code is silent about the content of steel, etc., or the material Fy, Fck, etc., in imparting the stiffness. So for 0.5% steel, it has shown this stiffness where it has the yield moment My1 and the yield curvature say phi y1. Let us increase the amount of steel, and now percentage steel is 0.75%. Corresponding yield moment is My2 and yield curvature is phi y2, which is different. Why it is different? Because the stiffness is not changing as per code. With the increase of steel, code says stiffness does not change. So this line is same for all cases. This will be a straight line here. Now we take the next case, which was 1% steel. The stiffness remains same. My yield curvature is higher. Yield moment is higher. Corresponding yield curvature is here. Similarly, for the fourth one, at 1.5% steel, the yield moment is My4 and yield curvature is phi y4. Everywhere, my stiffness remains same as the initial, because code says stiffness is not influenced by amount of steel or the strength. Okay, if the code was right, then one problem is there. The yield curvature is changing at every case. Yield curvature is more in phi y2, the second case, then still more in third case, and still more in the fourth case. But actual reality you have seen in the moment curvature diagram, the yield curvature does not change with this change of strength. So obviously the Codal assumption is not correct. Codal assumption of constancy of the stiffness being independent of the strength or amount of steel or Fck or Fy is not correct, because it violates this constancy of the yield curvature for a given section. So this is the actual behavior and this is the Codal behavior. So Codal assumption is not tenable. So let us see further. The stiffness varies with strength, as we have seen in the just last slide. The stiffness varies with the strength. If you increase strength, stiffness will increase as that angle is increasing and tan theta value will increase. So stiffness increases with the strength for a given section. So K varies. For the timing, we are considering strength to be the flexural strength, so K varies as M. And since M assumes at certain point the yield moment My, so K varies as My also. Now there is a term called the stiffness reduction factor. It is the actual stiffness divided by gross stiffness of the section. Actual stiffness means stiffness as you are getting out, giving the respect to the strength. That is, considering the strength aspect, you are getting the stiffness, which is, we shall say, actual. The actual will be less than gross, because gross is considering the entire section. So this stiffness reduction factor R can be called as effective stiffness divided by gross stiffness. In symbolic form we can write R equal to EI effective divided by EIG. Effective stiffness, how we have written EI effective, if we are considering the flexural case, then EI, the rigidity term, is always there. So we have written EI effective and EI gross. Now EI effective equal to MY by phi y. This why? Because in the moment curvature diagram, by definition, M by EI equal to phi. So M by EI equal to phi means M by phi equal to EI. So EI effective is nothing but My by phi y, yield moment by yield curvature. So finally, the stiffness reduction factor we can write R equal to My phi y from here divided by EIG. So this is the stiffness reduction factor. This you should use to reflect the actual stiffness of the system instead of the gross stiffness. So in the software like SAP 2000 etc., you have a way of giving the stiffness reduction factor for beam, for column and other sections, and this will give you the real stiffness based on the strength. Where from strength is coming? Strength is coming from this My value. For every system having some size, some steel, some FCK, some FY, corresponding yield moment will be different. So this you are reflecting at the strength, and phi y you are reflecting the constancy of the curvature, which depends on the only on the depth of the section. And EI gross is always constant. I gross is the BD cube by 12 for a rectangular section. And similarly for I section etc., you can find it out. So this is the stiffness reduction factor to be used for all members in the section before you run your analysis or design, so that, of course, before design you do not know MY, so you can run it in the analysis for knowing the non-linear behaviors. This stiffness reduction factor requires further inquiry, and we shall be taking this in the next video. Thank you very much for watching. Please subscribe the channel, like and share the videos so that it gets disseminated to larger group of audience. Thank you very much, and see you again in the next video.